Now, finally, we think about a more realistic model. It's called SIR model. Now, you had susceptible and you had infective. Now we consider the recovered. Notice that the recovered also contains the dead. Up to S2I transfer is the same logic. The infective comes into contact with the susceptible in a very small social distance. The susceptible that was in contact becomes an infective. So the disease spread like that. But then the recovered, the original carrier of the virus becomes a recovered person. So there's because of the immunity, if the virus comes again to this recovered person, this person becomes unable to transfer the virus. So it becomes the recovered population becomes an effective barrier against the spread. So the whole society do not get infected. How you model is really the same as before. But I must tell you that getting a solution is a bit more difficult. Actually, way more difficult. But writing down the equation is easy. So I should remind you that all you have to do is to think about these compartments. They actually call a compartment. Susceptible S is a susceptible compartment, and infective compartment, and recovered compartment. And we are shifting between the compartments, and there are some rates of transition from one compartment to the other. And we're already considering that. So now, from the susceptible compartment to the infective, as you know, this is what we have already considered. It will be proportional to S and I because of the contact. Contact requires two populations being in the same room. And as some of the population become infected, it will decrease the amount of S. So there goes the minus sign, minus RSI. Up to now, we have thought about dI dt, but now we are just writing down what ds dt. But, in the case of dI dt, RSI will be the increase rate, the in rate. But here, this is only the out rate, the decrease rate. And susceptible will go on just decreasing itself, right? And it will recover, will become the recovered population, but it will never become a susceptible population. You're never more naive. So this is an equation for susceptible. For the infective, we can write the same thing. So the in rate, as we have previously considered, will be R multiplied by SI. This will be the rate of increase of the infective. But then some of the infective will be spontaneously recovered and decrease. So it will be proportional to the amount of infective, and it is just multiplied it by some kind of rate of transition from I to R. So that's K. So you can write the whole thing as RSI minus KI. Notice that this reflects a spontaneous recovery, and you can see that this formulation is just the same as the leak, right? In our leaky water tank model, the leak rate depended upon the volume itself. It's the same thing. The spontaneous decrease of I depends on the amount of I itself. So if you move on to the next compartment, which is the recovered compartment, the increase of recovered population is just the same as the decrease of the infected. So it will be just Ki. So we have just three equations. But keep in mind that once again, for the fourth time, I repeat, you don't really have to think about how to find a solution for this. You just ask Mathematica or any software to solve it. And it's been out there already from 2011. So you go to a website called Wolfram Demonstrations Project. I put down the website address, and then you can download the Mathematica notebook that you can play with, and you also get a free Mathematica player, so you can just download it and change the parameters. And the parameters we can change are the number of social contacts per day, and then and you also think about the duration of infection. The duration of infection is the rate k. So if the k is fast, then you will quickly recover. But if your k is slow, then it will take more time to recover. And now you're writing it in terms of duration of infection. So this is the inversion of the rate. So basically, you're writing down 1 over k, and you change you slide this button, and you can change the parameters and see what happens, and then you can get to understand the flattening of the curve in a more realistic model. And now the contact number. Let's only focus on the contact number. In this model, we are considering that we are making contact with 5 people per day, which is reasonable. But if you do so, all the population drops down to 0, meaning that the disease will propagate within like 30 days. Everyone will be affected. And there will be a sharp rise of the people who are affected. But then, if you try social distancing by decreasing the contact number to 1.65, even for that small effort, you can flatten the curve. The peak of the newly infected people will flatten down quite a bit, and it will happen much later and spread throughout. So there will be less pressure on the medical system of the society. And also, if you do so, because some of those people who are affected will be recovered and become a barrier of protection, not all population will be affected. So if you just bring down your social contact to just less than 2 people per day, you can already ensure only about 60% will be affected. So this is the lesson. Basically, you don't have to be able to solve the equation, but by knowing how to understand the equation and make a mental picture of how the solution will be, how the quantities will change. And also, if you become able to ask the computer to solve these equations, you can get pretty far with your mathematics. This simple equation that we learned called the leaky water tank can find application even to tell you what will happen in the case of COVID-19 spread. And I hope that you understand at least 2 things that you see in the circulation of the SNS. You now understand why we have this interesting exponential growth in the initial phase of the disease spread. And now we know why and how the flattening of the curve can happen. The best way we can achieve the flattening of the curve is to decrease the social contact. So I hope that you stay safe, you take this lesson at home, and think about what you can do with similar application of the equation. And if you have any questions, just feel free to email me. Thank you.